Thanks for joining us. Thanks for joining us for the webinar today. I'm going to start off with a little bit of background on the Upper Esopus and the stream management that we're evaluating with our monitoring network. And then Don is going to present results from some reed scale monitoring, after which I'm going to present results at a little bit of a broader scale, taking a look at what we're seeing at the subbasin scale, so at the tributary level to the Esopus. This has been a 15 or more than 15-year now collaboration between the USGS, the Ashokan Watershed Stream Management Program, New York City DEP, and Ulster County Soil and Water. And I want to acknowledge Danny Davis from New York City DEP, who's our co-PI on the project. We've been working together for a long time, and it's been a great collaboration. And most of what you see today has been developed hand in hand, working together with Danny and others, with all of our collaborators here. And we appreciate the support for all of our research. So for anybody on the call that's not completely familiar with the Upper Esopus, it's the primary tributary to the Ashokan Reservoir, nearly 200 square miles in area, nearly 100% forested with a lot of protected lands, lots of DEC, wild forest, and wilderness, especially at the higher elevations. It's bounded by Catskill high peaks on most of the perimeter, with steep headwaters, thin soil over bedrock. So when we have large rain events between the high peaks and the steepness of the headwaters and that thin soil, the water tends to get transmitted pretty quickly down into the valley bottoms. So we tend to have very flashy hydrographs in this system. Most of the development is down in the valley bottoms where the road corridors are following the stream channels. And we have what we consider to be a glacially conditioned landscape. What we mean by that is there's a lot of glacial till and complex meltwater deposits in the valley bottoms and along the lower slopes. We're going to pay a special consideration for the glacial lakes that had formed here. There was considered one large glacial lake at one point during the last glaciation, and then potentially with advance and retreat of ice, we may have had some smaller lakes that formed in different parts of the watershed. And when those were present, we had a lot of fine-grained material that settled out into the bottom of those. And that's kind of what we're going to be concerned about and we'll be talking about in this presentation. So why do we care about managing turbidity? This photo on the right of the screen here is from Danny Davis. This is the Ashokan Reservoir after the December 2020 flood. So this storm and runoff event, because it wasn't just rainfall, we had rain on snow. This was approximately a 4 to 20% annual exceedance probability. And for those of you that aren't familiar with AEP, that equates to about a 25 to 5-year recurrence interval. So if you want to kind of convert back and forth, you would just divide your AEP into 100 to get your recurrence interval, or vice versa. So this resulted in elevated turbidity for 8 months in the tributaries and operational changes to the water supply for a few months after the storm. So one of the big questions that we have here is, can sediment loading to the reservoir be mitigated by some of the projects that are being done within the watershed? So we can try and lessen the effects of these big storms on the reservoir. And of course, there's also lots of ancillary benefits to biota and recreation and habitat and whatnot as well. So what are the sources of sediment to the streams? We're focusing primarily on the glacial lacustrine deposits. These I have a picture of in the upper left of the screen here. They tend to be more than 95% fine material. And you can see in that picture, when you get a chunk of this out of the ground and it dries out a little bit, you can start to peel the layers apart. So we have these layers of clay with a little bit of silt or very fine sand in between them. And you can imagine during a large storm how quickly these can erode. And once they're eroded and that material, that clay material, gets in suspension in the stream, it will stay in suspension all the way down to the reservoir and then stay in suspension in the reservoir for quite some time. Glacial till also has a fair amount of fine material, roughly 30 to 50%. But if anybody who's tried digging in glacial till before at home, trying to put in fence posts or something like that, you'll know how hard that material can be, especially if it's had a chance to dry out. So those exposures within the Esopus tend to be much more resistive to erosion than those glacial lacustrine deposits. Although I will say, during spring melt, if you have some water going over some of these glacial till deposits, you can get some material coming off from them, but it tends to be less of a source than the lacustrine material. Stream bank alluvium is another source that we consider, as it's ubiquitous throughout the stream channels. The thing with the bank alluvium, though, is that it tends to have very few fines in it. We're looking at, less than 3%, often down around 1% fine material. We also have to give consideration to forest soils and road runoff as sources, although from some of our other work, we know that those can be specific sources in places, but not as widespread as contributors as we would see with the lacustrine till or even the alluvium. So we're going to focus on those first three sources in our talk today. I want to talk a little bit about hydrology and disturbance recovery patterns in the watershed. We know that hydrology is the primary driver of the erosion and the suspended sediment and turbidity transport to the reservoir. And here we're looking at a hydrograph from Stony Clove Creek, one of the tributaries to the Esopus. So we have discharge on our y-axis here, and every point that you see is a 15-minute discharge value. And we're looking at the period of our study here. So, starting back before 2010 and then coming to the current time period. We also have the AEP values here for some select thresholds. We have the 50% is the lower dashed line. That equates to about a 2-year storm. So some people might consider that bankful conditions. And we think of that as the channel shaping event where we're not having substantial erosion. We are seeing the material get moved around. Maybe there's a little bit of alluvium being entrained from the banks, maybe coming from an upstream reach, but we're not seeing massive erosion. When we start to get above that 10% AEP into a 4 or a 2, within that range, we start to see significant erosion taking place. Those are those big storms where you're going to see the streams looking like chocolate milk and potentially staying that way for a bit of time if the sediment sources have been opened up. So we notice on this hydrograph that the period of 2010 and 2011, we had 4 storms that were greater than a 10% AEP. So we're considering that a hydrologic disturbance period. Then we have a fairly quiet period from 2012 through 2020, where most of our flows were actually below that 50% AEP with one storm that exceeded that threshold. Then we have a big storm in late December 2020 that exceeded that 4% threshold, and then going back again into another recovery period. And so we're going to dive into this in a little bit more detail on how this affects the turbidity a little bit later in the talk. So a little bit about the management that's done. Focusing on the sediment and turbidity reduction projects, we call these STRP for short. The goal of these projects is fairly simple. We are trying to disconnect the stream from those fine-grained sediment sources, so our lacustrine silts and clays, and primarily the clays. The images here on the right were provided by Danny. These are from one of the largest sediment sources within the watershed in Stony Clove Creek in Chichester. This was exacerbated by that high flow period, that disturbance period that we were just looking at on the hydrograph. The stream was coming in around a sharp bend here and eroding at the base of the slope, over steepening that slope. And then we had some subsurface and a little bit of surface flow as well coming down that was lubricating that material. And so we have this constant erosion at the base of the slope with more material coming down, and it served as almost like a conveyor belt of sediment to the stream. And you can see here, this is fairly low flows, And we have a very turbid stream there, a chronic source of turbidity and suspended sediment here. The project was done, and we can see one of the after photos towards the bottom there, and quite a bit of change. So how did we get to that? Well, in terms of the channel, in this case, there was room for them to relocate the channel to move it away from the sediment source. They constructed bank armoring on that outer edge to keep the stream from eroding back into the sediment source. Grade control was put in place, so large blocks of rock put in veins across the stream to prevent the stream from eroding back down again. Excavation of clay material when possible. Floodplain benches are installed to try and dissipate some of that energy out of the channel and into the floodplain. And then there's also work that's done on the hill slope. They can lower the angle. Drainage can be put in place to try and get some of the water away from the sediment sources. In some cases, in some of these projects, geotextile fabrics are used. And of course, the plantings, which are very important to help stabilize these sites long term. And not all of these different methods are used at all of the projects, but this is just a good example of some of the work that is done. So we had multiple projects done in Stony Clove from 2012 to 2022. There were some additional projects in Woodland Creek, as well as Beaver Kill. And Don and I are going to focus on some of those projects in Stony Clove and Woodland today. And you can see that picture I have at the bottom here. These are not small projects. They're bringing in large equipment and very large quarried rock to help stabilize these stream channels. So with that, I'm going to turn it over to Don for a few slides to talk about the reach scale effects of the projects.
Thanks, Jay. So to build off these STRP reach projects, the USGS operates an intensive turbidity sensor network in the Stony Clove Creek watershed. And when it comes to evaluating the impacts of STRPs on water quality, this network is going to be one of our best tools. So Warner Creek is the largest tributary to Stony Clove Creek and is a stream with multiple unstable reaches where fine-grained sediment is accessible to the active stream channel. Now, in late 2021, 2 STRPs were implemented to address one of these unstable reaches. So here on the right here, we have results from 2 USGS monitoring locations that bracket the project reach. The data that we use here is continuous 15-minute turbidity data. And we divide that data into 2 time periods. One that is a period of data collected from before the STRP, and one that is collected post-STRP. So looking from left to right on this figure here, we have the pre-period data distribution for the downstream Warner site, LWA. We can think of that as lower Warner, the downstream site of this STRP. The second box plot is the post-period for the downstream site. The third is the upper site pre-period, pre-STRP. And then finally, the fourth box plot on the right there is the post-period for the upper site. So I'd say the first takeaway here is that turbidity data that we're showing here between the pre and post-project periods shows statistically significant decreases for both the upper and the lower site. It's worth noting the upstream site, which is above the effects from the stream project, experienced a natural reduction during this time. It's likely the downstream site also experienced this reduction. However, overall decreases are more than double that was experienced at the upper site. So this is pointing to the impacts of the STRP on water quality. And one last takeaway I'd like to take from this figure, if we look at the pre-project box plots for the lower site and the upper site, as we see, so that's the going left to right, the first 2 box plots, we're seeing a lot more variability from the pre-project box plots from the lower site compared to the upper site. So this is not surprising. We know that the lower site was impacted by turbidity sources within the project reach. If we look at the post-period box plots, what we're seeing here, so this is 2 and 4. we're now seeing a much tighter, similar distribution of the data between the upper and lower sites. And this is indicating that turbidity sources in between the two sites in that STRP reach have been minimized through the project construction. So we've established that turbidity generally decreases at the lower and the lower downstream STRP Warner site and the upper site as well. Can we additionally dig into this a little more, and can we demonstrate how turbidity was affected across a full range of discharge conditions for these two periods? So here we paired 15-minute turbidity data with also 15-minute discharge data. We then ranked and grouped the data according to that discharge data. And after the data was grouped to reflect these different discharge conditions, we compared the corresponding turbidity data. So if we look here from, let's go right to left here. Here we have the greater than 50% and the 50 to 25% exceedance flow classes. So if you want to think of these discharge classes, think of these as your, for the most part, everyday flows, including non-storm periods and summertime low flows. As you can see here, decreases exceeded 30% and are indicative of decreases of what we usually call chronic turbidity production, which occurs during these low but long time periods in regards to looking at the overall hydrograph. The next two groupings of box plots, the 25 to 10% and the 10 to 1% exceedance groupings. So these represent your above average elevated flows that are typically snowmelt or your smaller runoff events and falling flows after large runoff events. So here we see reductions that exceed 60%. And this is usually what we call decreases in what we think of as episodic turbidity production, which occurs during these runoff periods. And then finally, on the two groupings of box plots on the left here are the 1 to 0.1% exceedance grouping, and then the less than 0.1% exceedance grouping. So these are your highest of runoff events here at Warner Creek. And typically these are runoff events from your intense thunderstorms or wintertime rain on snow events. So these are the conditions that we really care about, because this is when the stream transports the most sediment. This is when turbidity production is at its greatest. And this is also the most likely period where local turbidity production will impact downstream water quality. Reductions here exceed approximately 30%. What we should know is that the 4% AEP event that Jay referenced earlier in December of 2020, this was during the pre-project period of the data groupings. Post-project, here at Warner, the project has not yet been tested by a runoff event of this size. During the relatively hydrologically calm post-project period, only one storm at this time has exceeded the 50% AEP level. So here's a second example of the effects of an STRP on water quality at the reach scale. So we're going to go to the other side of the upper Esopus Valley to Panther Kill, which is a small steep stream that flows into Woodland Creek. So here we're going to be looking at the same figures we just looked at, but for Panther Kill. So the water quality situation here was definitely different than the Warner sites that we just looked at. Comparatively, if you look at the scale on the y-axis of this plot, the turbidity conditions and the turbidity reduction were much greater in this stream reach. So the pictures on the left here kind of give you a good look at that. Panther Kill used to make extended contact with a failing bank of fine-grained sediment. So that's that upper left picture there. And additionally, lacustrine clay was mass wasting right into the channel, and there was also lacustrine clay found in the bed of Panther Kill at this location. So in late 2022, a project was constructed, resulting in that second lower picture that we have there. The overall turbidity results, as we see in the box plots here to the right, show statistically significant reductions at the monitoring locations above and below the project. Similar to Warner, if we look at the upstream Panther Kill site there, a natural decrease existed. The lower site, once again, similar to Warner, probably also has that natural reduction, but there was a much more substantial decrease that was the result of the STRP and the removal, basically, of the connection between the stream channel and the fine-grained sediment. And then also, like the Warner site, we can break it up by by discharge groups. Once again, going from right to left in the plot. If we look at those greater than 50 and the 50 to 25 discharge exceedance groupings, which once again are representative of your more or less normal everyday flows, we see 75% decreases in turbidity. And so these reductions show a large magnitude reduction at, like we said before, that kind of chronic turbidity production level for water flowing out of Panther Kill. For the next two groupings, the 25 to 10 and the 10 to 1% discharge groupings, we also see a 75% reduction in turbidity, showing that the relative reductions in episodic turbidity match the relative reductions seen for the chronic turbidity. And finally, that 1 to 0.1% and that less than 1% discharge exceedance groupings, that first grouping, the 1 to 0.1%, shows a statistically significant 50% reduction. However, a non-statistically significant 6% reduction at that highest less than 0.1% discharge grouping. So it should be noted, similar to Warner, that top flow class, for the period of data that was collected, that this was the largest storm for the period. And in this case, so that means for that pre-grouping and that post-grouping, it was essentially one storm of each because we only had 3 years of data here. And large in this case is only a 50% AEP runoff event. So this is still, like we mentioned before, a large bankful channel shaping event, but it does not approach the discharge levels seen at this watershed in previous years. So like Warner, future storms will test the integrity and efficacy of these reach scale stream projects in regard to turbidity reduction. But that being said, the one takeaway we can definitely take from this figure right here is that Panther Kill, turbidity at Panther Kill was dramatically and statistically significantly reduced in excess of 50% and often 75% for all but the upper 0.1% of discharge. And with that, I'll turn it back over to Jay.
Thanks, Don. So as Don had mentioned, we had some natural recovery that was measured, or natural reduction in turbidity between the pre and post projects at the upstream sites above where the projects were constructed. So we wanted to take a little bit of a look at an example of natural recovery in a stream that had substantial erosion, but did not have any projects put in place. And so Hollow Tree Brook, which is a tributary to Stony Clove, serves well for that. We have a pre-disturbance period here where the median values from 2016 through 2020 were only 3.4. So very low turbidity coming out of the stream for a period of about 4 years. Then we have that large December 2020 runoff event. And we can see that dramatic increase where the median is now up to 245. And that box for the disturbance period represents about 5 months after the storm. And I'm reusing my picture of Danny here from earlier in the talk to demonstrate what Hollow Tree Brook looked like within part of the reach, where a substantial amount of erosion occurred as the stream went into a different channel. And you can see here we had these large clay banks and clay on the beds. So this is basically a clay canal that the stream was going down. So then we have an initial period of recovery, which would be about 6 to 8 months after that runoff event, where the turbidity levels came down to about 38, so nearly an order of magnitude decrease through natural recovery here. And we know that that took place from some alluvium being brought back into the system, from the banks, from upstream, some of the smaller, near channel shaping flows that were bringing that material in provided a very thin armoring layer over that clay material. So then we did see continued recovery down to 15 FNU, but never getting back to our pre-disturbance levels. And so this is something we're going to want to keep in mind when I talk a little bit about Woodland in a minute. And this is the site of a future STRP. I'm going to use Stony Clove Creek to describe some disturbance and recovery patterns. I'm probably trying to go through these slides a little quick for the sake of time. A bunch of these are going to have the same plot, so I'll just take a second to describe this. We're looking at daily mean turbidity as a function of the daily mean discharge. The green points on all these slides will be recovery periods. The red points will represent disturbance periods. And what we really want to get out of these plots is the change in that relation between turbidity and discharge between the periods. So we're starting off here with these red points, our disturbance period for runoff events greater than the 10% AEP, including Tropical Storm Irene, greater than 2%. And we had very high values here. Even at the low end, we're approaching 100 for mean values at low discharge. So this was a big chronic, there are a lot of chronic sources, very large sources after those storms. We then have a long recovery period that we kind of grouped together here, where there were 8 stream projects done in the watershed and some natural recovery. And that other researchers have also noted that both the projects and natural recovery have teamed up to kind of give us some reduction here. And when we look at our data during this recovery period, we can see more than an order of magnitude decline in turbidity values through the range and discharge. One thing to note here is that there's a lot of variability during that recovery period, and we're still seeing the occasional high values at that low end. So we still have some chronic sources within the watershed. So same recovery period from the previous slide. Now we're looking at another disturbance. We had that big December 2020 storm. Again, turbidity was elevated for 8 months. We had a nearly order of magnitude increase in turbidity as a result of that runoff event. The photo on the left here shows some of the damage done in Stony Clove Creek, where part of Route 214 was washed away. This was also the location of one of our monitoring sites, which was no longer there after the storm. And so you can see the turbidity here. There was a lot of damage in the watershed. So we want to take a little bit more of a deeper look at what happened during that storm in the watershed. So Danny and others had gone out and mapped the stream channel in Stony Clove and its tributaries prior to that event as part of our long-term research projects. They mapped where erosion was taking place and the material that it was eroding into, whether it was alluvium, lacustrine, or glacial till. They also were able to do this in those same stream reaches after the storm, so we could see the changes that the storm resulted in. We had a 3-fold increase in observed erosion throughout the watershed. It was proportionally greater in the lacustrine material, which of course is problematic because that's the material that's going to stay in suspension to the reservoir. And we noted that it was primarily coming from untreated sources. They were not mapping much re-engagement of the stream with fine sediment in those STRP reaches. And also our turbidity data agreed with that. When we looked at our above and below data, we didn't see large increases in turbidity from those project reaches, which is good. So 2 lines of evidence saying that the projects were working, the sediment was coming from other parts of the watershed. Another way to look at the resilience in Stony Clove is to look at some Google Earth images. Danny provided these to us with the stream channels outlined. It may be a little bit hard to see on some of your screens, and I apologize for that. Starting in the upper left, we had the channel before the projects were done. And if you look in the middle of that, you can kind of see that bowl-shaped feature near the sharp bend. That's where that large sediment source was that I showed earlier. Then we have the project that was done. So the middle picture here is after the projects, and this whole stream reach within this image here was reconstructed, including the bed. And of course, you can see where the hill slopes were treated as well. Then the lower image on the right is what it looked like after the storm. And just note here that the brown you see on this image is from dormant vegetation. It's not sediment sources. The important thing to note is that this channel did not adjust as a result of that storm. We did not see large areas of erosion where the channel was moving out of that constructed channel. So it was resilient to that 4% AEP storm and kind of did what we wanted it to do in the way it was designed. Although there was some aggradation in some areas where we did see some deposition of cobbles and whatnot. So final slide here for Stony Clove, and then I'll go through Woodland. We're going from that previous disturbance period back to another recovery period where we had 3 stream projects, one of which was the one that Don had talked about in Warner. We had some natural recovery, so we see that shift down in the relation. We're getting less turbidity for a given discharge than we did during that disturbance period. The important thing here to note too is that we have a lot less variability in this recovery period than we saw in that earlier recovery period, especially at the low flows. We're not seeing those high turbidity values anymore. So more of those chronic sources within the watershed have been shut off with some of the projects that were implemented. So same setup here with the plots for Woodland Creek, but the difference here is that we're starting with a recovery period. So in 2017, we had a period of what I would consider to be natural recovery, very low turbidity values. However, we do know that there were a lot of fine-grained sediment sources in this watershed. They were all covered with a very thin layer of alluvium. Then we had a disturbance on October 30th, I believe, of 2017. Not a very large one, though. This was only a 50% AEP runoff event. So, what we might consider typical bankful. This stripped the armoring layer off of those clay sources. And you can see that in the photo on the left here from the upper reaches of the main stem of Woodland Creek. So that armoring layer was removed, and the stream is right back to being on top of the clay, which resulted in nearly an order of magnitude increase in turbidity levels. So same disturbance period on this slide. We have a recovery period. Oops, sorry, I went backwards on that slide there. Pardon me for that. Here we go. So now we have that same disturbance period from the previous slide, and we are now looking at a recovery period where we had a stream project in the upper reaches of woodlands. So the stream is no longer in contact with those sources, including that one I showed on the previous image, and some natural recovery resulting in substantial decreases in turbidity through the range in discharge. And now we're going from that recovery period back to that December runoff event. In Woodland, this is only a 20% AEP event, so a little bit smaller than in Stony Clove, though we did see, especially in Panther Kill, there was substantial erosion that was happening. And you can see on the image here, on this figure, that we had this dramatic increase again in turbidity levels through the range in conditions. And our final slide here for Woodland Creek, looking at the patterns of disturbance and recovery. We go from that previous disturbance, then we have the project that Don talked about and gave us the details of what we were able to measure at the reach scale. Down at the outlet of the watershed here, we did see between that project and some natural recovery, another decrease in turbidity values, again, through most of the range in discharge. And so I think this is a good comparison when we think about that natural recovery we saw in Hollow Tree Brook, just based on a thin layer of alluvium that has covered up those sediment sources. We can look at those first images that we had of Woodland Creek, where there was a natural recovery period, again, with just a thin layer of alluvium. It may not take much to strip that off of those sources again in Hollow Tree, and we may end up back to that being a high turbidity producer once again. So to summarize some of our key points here today, the projects we know can significantly decrease connectivity with fine-grained sediment. We map it beforehand or more accurately, Danny and other folks from DEP and Ulster County Soil and Water have mapped these streams. And we know how much material the stream was in contact with before the project. And in theory, the projects are completely eliminating all of that contact. So we know that they can be successful at that. We also know that they decrease turbidity production through the range and discharge up to some of the higher values that we were able to measure during our studies. Of course, for some of these, we're still waiting to test them at some of the higher flows. We know that these projects can also enhance the resiliency of the stream channel network and aid in natural recovery in the system. And we showed that with both the mapping that's been done and with our turbidity data bracketing some of these projects. When we had that Christmas storm in 2020, we know that there wasn't sediment or there was no substantial sediment being generated from those project reaches. It was coming from some of the untreated reaches in other parts of the watershed. So again, we know that the non-treated sediment sources drove that turbidity production during that large event, not the project reaches. And our evidence indicates that the implementation of these projects really can help decrease turbidity production during runoff events and shorten that post-storm period of high production. And that's important here because we know that future big storms are going to interact with some of those other sediment sources that are untreated in the watershed. So we're still going to see some large pulses of sediment being delivered to the reservoir. However, our results suggest that these projects can help take off kind of the top end of that, reduce the magnitude of the impacts on the receiving waters, and also shorten the amount of time that those receiving waters are going to be affected by the results of these large runoff events. So some of the next steps that we're going to be working on this winter as we wrap up our projects and get our final products out, we're going to try and estimate what the concentrations and loads would be with no mitigation in place, which is going to be tough because it's a chaotic, complex system. We're going to do a more detailed analysis on subbasin and reservoir scale turbidity, very similar to what Don did at the reach scale, but looking more broadly through the basin. And we're also going to identify locations that have the greatest potential for future connectivity of the stream with the fine-grained sediments. And we're doing that through some remote sensing work and some geophysical analysis of the extent of the clay material within Stony Clove and Woodland Creek. And so I think with that, I'm going to exit presentation mode. And if anybody has any questions, if we have time for questions and discussion, I can go bring us back to any specific slides folks would want to take a look at.